ML is everywhere, but it's like starting from perception and more moving to prediction. And I think where the cutting edge is really is in the planning and control side. So how do you bridge these gaps from pixels to steering? So ML is everywhere. Of course, I'm biased. But...
You're listening to Gradient Descent, a show about machine learning in the real world. And I'm your host, Lucas Bewald. Adrien is exactly the kind of person we imagined having on this podcast when we started it. He's the head of research at TRI, Toyota's research arm, and he's been a long-time user, maybe one of the very first users of weights and biases. And every time I talk to him, he has interesting ideas on the field of machine learning and the tools necessary to make it really work in production. So this is going to be a really interesting conversation. All right, so I have a whole bunch of questions, but I thought I'd start with a little bit of an oddball one, only for you. So I always use this metaphor, building the weights and biases tools, that I hope our users love our tools in the same way that a guitar player loves their guitars. And I know you are a guitar player. Do you have a favorite one that you own and play?
Right there.
Nice.
I don't know. I need to deactivate my Zoom background, but this is a road-worn Fender Strat.
Oh, beautiful.
I love the road-worn because first, I don't mind damaging it more. And second, it has a really nice feel. I think tools, that's more general than just guitars, but they grow on you. It's kind of like, it's almost like, a lot of musicians give names to their guitars, like Eric Clapton famously, etc. And I think really good tools, they become part of you and you develop a relationship with them. So it's the case for cars, it's the case for guitars. Virtual tools, it's kind of interesting. Some tools definitely become part of you. I haven't named a WNB report after my daughter or something like this yet, but who knows?
Well, besides WNB, what are your favorite tools that you use in your day-to-day job building machine learning models?
So if you're talking as a manager, that's not the same as if you're talking as a scientist.
Ooh, answer both, please. I would love to hear both.
All right. So I won't mention maybe the ones that everybody knows and love. And I like Todoist a lot as a manager. That's a great way to manage your tasks and stuff like this. I've been a long-time user of Todoist, and I really, really like it. Tried a lot of different ways to manage to-dos and etc. and keep track of this. They even have karma points and whatever, things like gamification. So this one, I think, is a pretty nice recommendation I can give to everybody that has a lot of tasks and want to stay on top of them. So as a manager, this one is good.
And what do you like about it? As you said, Todoist is the app. We should put a link to that.
It's Todoist.
Todoist.
Yeah.
And in one word. What's good? I have to say, I use Workflowy, and I'm super attached to it myself. I'm curious, what do you like about Todoist?
It's very simple. So I think tools, in this complicated world where you have many things to do, has to be dead simple. And good synchronization across devices is also super important, because when you switch from one to the other, etc.
Nice. Well, this show isn't for managers. It's for the scientists. So tell us about, as a scientist, what tools you love.
So for the scientists, I mean, Jupyter notebooks, super, obviously, right? I said I won't mention the ones that everybody uses and loves, but this one still, I will mention it. Otherwise, I mean, PyTorch is just awesome. As a manager and now senior manager, I get less and less time to do technical stuff, as it should, right? I focus on empowering my teams, etc. But I still have this itch, and sometimes, I do a lot of code reviews and I'm like, oh yeah, I want to try this thing. And so PyTorch, even as a senior manager that doesn't do 50% or even 30% of his day coding, I still get back to it very, very quickly, because it's just so simple, very few abstractions, very little vocabulary. It's not a DSL, right? It's NumPy. It's NumPy on steroids, and that's just so easy to use.
Interesting. Can you say anything else about PyTorch? I'm always kind of curious. PyTorch just seems to have these passionate fans among our user base. The people that use other frameworks, they use them a lot and they seem to like them, but somehow the people that use PyTorch seem just incredible advocates. Do you have any sense of why that is?
So I've been working in computer vision since 2007. And so basically in 2012, I finished my PhD, and then I moved to research in industry at Xerox Research. And then what was interesting was that was just the time. So I was big into kernel methods. Everything had to be convex and learning theory, Vapnik, super clean and then 2012, Krzyzewski, non-convexity, not a problem, all these kind of things. And Café was very big, became very, very big, especially 2013 with Ross Gershik and Berkeley doing amazing work there, Yongqing Jia, et cetera, et cetera. So all these kind of tools really born there. But Café is C++ library. fairly easy to reproduce things, but fairly hard to do your own like fork and do something very different, especially in the learning algorithm, like not changing architectures, etc. That's the easy part of deep learning, but changing the task you're working on or changing the overall learning algorithm is more complicated. And I maintain an internal fork of Caffe, and we did some papers, etc. But then like, and the alternative was Theano, which was like, let's say an early days pioneer, and I will leave it at that. A great library, but not necessarily the most user-friendly one. And then TensorFlow came, and there's this huge hype train, right? Of like Google, everybody wanting to work for Google, like TensorFlow. So of course, jumped on the bandwagon too. And then LuaTorch was the only kind of like asterisk a little bit, like the little village like of resistance to the Roman Empire. But I never really liked Lua. I was always a big Python fan. And so when PyTorch came out, like the nice clean design of Torch with Python, that basically became a no-brainer. And everybody was that did Python, like PyData, kind of like Sphere, like SciPy Sphere, like it was familiar with NumPy, immediately became familiar with PyTorch. And that was the genius, right? No training, no onboarding. You know NumPy, you can use PyTorch. I'm psyched for JAX, so it's kind of interesting because now Google kind of realized this, that the DSL, graph-based, like very complicated ecosystem, like very complete ecosystem. So really nice for production setup, but for researchers that are a bit more on the crazy side of things, I wish I had the time to play with JAX, basically. I just looked at things and it sounds amazing. And I think maybe there's going to be more diversity on PyTorch-like tools. So
it's so interesting. Like, I think when TensorFlow came out, I thought, oh, people just want to use the same tool and everyone's just going to kind of switch to this. It's been kind of surprising to see the passionate advocates of PyTorch. At least by our internal metrics, it seems like it's getting more popular. Do you have any sense about what it is about the design that makes it feel so satisfying?
Right. So there is a really, really great paper at NeurIPS last year, if I remember correctly. I think it's already cited 1,500 times, so which is huge. Like for a paper to be cited more than 1,000 times is a big, big deal. So in less than 1 year, it just shows you how popular it actually is. So it's by the PyTorch authors like Sumit Srintala, et cetera, so all these great people. And they describe their design principles in that paper. So I can recommend to you listeners to check it out. It's very accessible. It's a NeurIPS paper, so it might scare people away. That's math, but it's not. It's really, really good paper to read. So I won't summarize that paper, but the design principles are really, really good. And they are basically directly the result for me of the great UX. It's the user experience, right? Is that just, you can't force people in this age of open source and of free tools that are widely available and also widely known, right? Like it's like you have to live under a rock to not know PyTorch exists, right? Then, the best user experience wins. It's just as simple as that. And PyTorch is just so few abstractions. I think it's like maybe 4 abstractions total that you have to know. That is PyTorch specific, right? And again, the rest is just very, very generic, very powerful, has nice workflows. There's PyTorch Lightning that tries to simplify those workflows, like maybe Keras style, like high-level APIs. But just the base level one is just, you go from idea to experiments really quickly. So that would be my why.
I love the idea of user experience of a library or like a deep learning framework. It's like you normally think of user experience as like a website, but the developer user experience is so important. I totally agree.
Yeah, and it's because basically just like coding, right, is becoming democratized. Right? There's this huge thing about no code, right, which is all about that, right? But code is still like, people are going to code for a long time. It's like, people say, oh, no code, people will stop coding soon. No. Same thing as like self-driving cars. Yeah, they're going to happen, but it doesn't mean that people are going to stop driving soon. So there is kind of a lot of like good things that can happen if you simplify the user experience for what used to be called power users, but like it's the 70s era is done where only the most hardcore geeks code. Everybody codes now. So a lot of people code. So.
And I guess you're more than a researcher, right? You've been working on autonomous vehicles at Toyota, trying to deploy them for quite a long time, right? So, I think some people might worry that PyTorch isn't easy to put into production, but you have one of the biggest challenge of productionizing your systems. How have you thought about that? Does PyTorch work for you in production?
Right. So TRI was Toyota Research Institute, where our work was created like in 2016 roughly. And so we haven't worked that long on it, like compared, let's say, to the Waymos, et cetera, that like really started in 2009. But what's fun is that we kind of started with PyTorch almost from the start. Like we did at first, like the first year, we were really working on TensorFlow, mostly for that reason that you're describing, is like putting things in production, et cetera. But we found out that iterating was actually a bit painful. And because the decision was within our power, us, the researcher, we kind of switched to PyTorch fairly quickly. So that was one of the decisions I made early on that we're really happy with. The downside to it is like when you're on the bleeding edge, you have blood all over your fingers. You cut yourself, right? And especially on the production side. So in the early days, what it meant is that, well, you deploy something, like in Python or something like not glorious. I don't want to go into the details because it's a bit like, but then as the ecosystem progressed, right? And now, like, especially I would say in the last year or so, PyTorch has really been like growing in its focus on productionizing. It turned out to be a really good bet. Like, we did it from a research perspective and a velocity of iteration because, that's our stance, is like autonomous driving, still a lot of research problems to be solved, right? A lot of research. So you want to optimize for the bottleneck, right? It's something very well known in the Toyota production system, this theory of constraints. You look at, your workflow, where's the bottleneck? And optimizing the rest doesn't really matter because it's still the bottleneck that governs the speed at which you iterate. So we found that experimenting was the bottleneck, and now like production is not a bottleneck anymore because there's great tools like Onyx. So we're using Onyx, we're using TensorRT as part of our tool chain to deploy like models that are efficiently running on GPUs, etc. There's even more recent projects from NVIDIA like TR-Torch, which enables you to go directly from PyTorch to TensorRT. So, and there's many more like for beyond NVIDIA hardware. There's like exciting like cross compilation tools, like things like the TVM stack, et cetera, et cetera. So production wise, I think it's such a big deal to deploy models that if the second top framework or the top two frameworks don't have good solutions for that, they're doomed to fail. So they understood this a long time ago, and it's good now.
And so you're saying today though, you actually can do it. Like you can get it into production. It's not a problem.
Oh yeah. I mean, we could do it before. It's just not necessarily very nice production engineering, but now there are tools to do this in a really state-of-the-art way, not just by researcher standards, but by proper engineering standards.
Right. I feel a little reticent to ask you this question because probably everyone asks you this. This is what my parents ask me, but like in your view, since you're at the front lines, like what is the state of self-driving cars? Like I feel like everyone talks about it, yet I can't get into a car and tell it to drive me somewhere and have it do it. On the other hand, I live in San Francisco and I see these cars driving around autonomously all the time.
Right.
What's going on?
Yeah, that's a good question, right? So that's a standard question. That's a question everybody should ask themselves every 6 months or so. And the question is for how long? That I don't know. I can't predict the future. But I think that one thing that attracted me when I came to TRI was I was just surprised how much people thought it was solved. Like back in 2016, when I really started working on autonomous driving, it was kind of like, as a researcher working in computer vision and machine learning, I was like, I'm excited about a lot of exciting problems, like how do we leverage the fact that labeling is expensive? So we want to optimize the label efficiency, maybe even go self-supervised and these kind of things. And it was just starting at this period, or using simulation, right? So one of the big things I've done is leveraging simulation. And I was like, wow, there's so many open research challenges. It's so cool as a researcher. I have a huge playground and a huge societal motivation to actually solve, like there's 1.35 million traffic fatalities every year on the road. So I was like, this is a huge societal problem. It's super important to solve that because it's 1.35 million is just crazy. But the reason that it's so high is because it's so hard. And so it's super hard problem, super important. And there's so many research problems. So as a researcher, super excited. Move to Bay Area, everybody's like, it's in 6 months. And in 6 months, I got this. Everybody from this little startup to the big companies to OEMs, everybody was like coming up with dates. 2018, we got this. 2016, 18, 19, 20. I mean, you name it. Go back in 2016 and listen to any announcement or etc. You will see everybody promised everything every time. And it's to get VC money and everything like this. I know it's Bay Area, I get funding. But the stance, like Gil Pratt, our CEO, which is a former DARPA director, he was an MIT professor and everything. So he's very, very smart and very like an excellent roboticist. And he had always a deep appreciation for the problems. He was at Bell Labs and all kinds of things. And so it's always been like, it's much harder than people think. It's going to take much longer than people think. And therefore, if you're serious about it, you should be committing long-term resources and treat it as a research problem. So we are a research institute. Research is our middle name. Like John Leonard, a famous robotics professor, is one of our VPs, always says that. So it's going to take a while. It's going to take a while. And people are now coming to this realization. Because in spite of all the hype and everything, when the results are not there at the given time, well, you have to face the facts, right? And so now what we're seeing is we're seeing a consolidation in the field. It's like people that are really committed to this problem long-term, they're willing to sink in the money, the time, et cetera, and maybe open their minds a little bit to, hey, it's research. So we, for instance, need like strong partnerships with academia, which we work a lot with Stanford, MIT, and University of Michigan for those reasons. We don't know all the answers. So we got to work with people that also don't know the answers, but can like take the scientific approach to try to figure them out versus just say, it's solved, We just need to throw 100 code monkeys or 1,000 code monkeys or 10,000 code monkeys at it, and it's going to work. I think that's not the case. And even the engineers at these companies are actually doing a fair amount of research, right? Even in the engineering heavy companies, I think. So
I was telling our Slack community that I was going to interview you and asking them if they had any like questions they wanted to ask. And I thought one of the really good ones was, it's a little bit general, but you're kind of alluding to it, is what are the big academic advances coming that'll kind of change the game for self-driving cars? You seem like the perfect person to have a perspective on this.
One thing that I'm particularly excited about and that I've been doing some work on is differentiable rendering. There's this huge, ambitious vision. I think the academic professor that I think embodies this the best is probably Josh Tenenbaum at MIT. This is a really, really amazing professor. If you don't know about him, just check out his research. And him and his student, Jiajun Wu, who's now a professor at Stanford, we're actually like discussing with them and they have super cool ideas around this vision as inverse graphics program. And I think that's really the right way to frame the problem. Alan Reel, another really interesting professor, was basically calling this analysis by synthesis. So the idea is that what you want to do is, with deep learning right now, which is fully supervised, is just you're learning a function that says, here's an image, like you say jump, I say how high, right? It's like, here's an image, cat, dog. Just say cat or dog. Cat, wrong, that's a dog. And you do that thousands and thousands of times, right? It's not unlike how we teach, like how I was teaching my daughter colors, it's like red, yellow, no, it's red, blue, no, it's red. And you do this kind of, then it kind of exponentially takes off and they become much smarter in their learning. But this initial phase of learning, which is rote memorization, kind of like this is how deep learning works. The problem with that is that interpretability, data cost, like lots of problems around that. And so for vision, what's interesting is the world has structure, right? And there's physics, like Newton existed. There's a physics of like there's gravity, there's physics of light. There's a lot of like inductive biases that you can leverage. Like you can take basically this physics and physics laws and then try to bake it into your learning approach. And differentiable rendering or inverse graphics is one way to do it. So basically, to take your sensor, you're trying to deconstruct the world and resynthesize it. And that way you can compare you in a self-supervised way, like what you reconstructed from what you observed. And the benefit of that is that you get systems that generalize much better, that can be trained on arbitrary amounts of raw data, don't need labels. And they also have some interpretability to them. They have some structure, right? Because they're deconstructing the world and following some structure, etc. So differentiable rendering is a big one for me. Vision as inverse graphics is a big one. And there's many others, like self-supervised learning in general is something I'm very excited about. And it goes beyond just differentiable rendering. There's many other ways to leverage self-supervision, especially time. When you look at video, like the temporal dynamics. Contrastive learning is a super hot topic right now. And there's interesting works, I think, from Max Welling's lab called the contrastive structured world models that I think is a cool paper, like not really like super applicable like right now, but I think like an exciting idea. And yeah, I would just leave it at that. Vision as inverse graphics, self-supervised learning. I'm super stoked about that.
I hadn't heard of contrastive learning before. Could you describe that briefly? You did such a good job with the with the other topic.
Right. Well, I mean, so overall, in a simple way, I would say that contrastive learning, so there's a really cool paper that I can recommend everybody to read, which is the paper from Godfather of Deep Learning, Geoff Hinton. It's called SimClear, SimCLR. And it explains a little bit in like, it got state-of-the-art results. Basically, there's two big approaches in contrastive learning that work really well. Is SimCLR and Moko from FAIR, Kai-Ming He, another super impressive researcher. And the basic idea is it's some form of metric learning, if you want. Is like you basically want to learn a representation that verifies some ordering property or some distance property. Something like, here's a traditional way would be, here's an example, here's one that is close to it, and here's one that is far from it. And what you want is you want to learn the properties of your representation such that this is true. And in a very simple way. And in general, it's like related to metric learning in general way. But the cool thing is that, for instance, in this CSWIM paper, contrastive structured world models paper that I was mentioning, you can look at it as temporal dynamics is one way, like things that are close in time should be close in representation in feature space, and things that are far should be further away. It's not always true. And actually, we have an ongoing work with Stanford, a paper called CoCon, Cooperative Contrastive Learning, where the idea is in some cases in videos, things repeat themselves. And so you want to basically leverage multi-view relationships such that you know that the same thing in multiple views should also be closed. So it's not just contrastive learning, but also like cooperative. And but it's an exploding field. There's so much work on that. The cool thing about it, Seem Clear, etc., was shown that you can replace pre-training on a large label data set, like ImageNet, by just doing unsupervised pre-training with contrastive loss.
Wow, super cool.
Yeah, and in practice, it's a big deal because, for instance, like we can't use ImageNet to deploy a product. So if you're wondering like, oh, I can just easily take an ImageNet pre-trained model, get a few labels, few shots, transfer, and use it. Well, for production, you can't really do that unless you have a license, a commercial license or something like this. So being able to do unsupervised pre-training, which was one of the early inspirations of deep learning, with restricted Boltzmann machines and whatever. You want to do unsupervised pre-training with a lot of data for a lot of time, and then very quickly fine-tune with a few shot setting, like a few labels. And it seems like we're there now.
Very cool. All right, switching gears a little bit, I just want to make sure I ask you this question, because you were telling me that you listened to our interview with Anantha, who's a VP of engineering at Lyft. Yeah. And I think he brings maybe a different company's perspective, but maybe also he kind of came up through engineering and thinks of himself, as like an engineer.
Right.
And I was kind of wondering how your answers for those same questions about taking autonomous vehicle to market would differ from what he said.
One thing that I take from what he said was he talked a lot about like the organizational aspect. I think that was really interesting because when you think about engineering and you think about a problem like self-driving cars, it's not a one-man or 10-man team, right? Like, or woman. It's not 10 people effort. So the challenge is it requires a lot of people and a coordination of a lot of people. Also, it's a robotics problem that is pretty wide in the skill set that it requires. You have from people like hardware, like we have amazing like hardware people at TRI, which is like kind of like it always impresses me because I can't use a solder iron, like even if you put a gun to my head. But these guys, they are magicians, So you have like really good hardware people, you have cloud people, you have like all kinds of different skills. And one thing that I remember was in that podcast was like ML is a skill, right? ML is a skill that is to be shared with everybody, and so that's why it's kind of like diffused in the company to be successful at deploying this. I think that's a really good point. I agree. I would add something to it, which is because I lead a machine learning team, right? So there is such a thing as so even though it's a skill and it should be everybody has it, I actually lead a team called machine learning, right? Machine learning research. And so if it's a skill and it's diffused, why have a team that's like this? And we iterated through a couple of models of like, we're kind of like experts, and then teams can basically request projects where we help. So we kind of like embedded in other teams. But that was not necessarily super successful. So we basically got back to we do our own projects, and we try to then seed some kind of like more crazy ML projects that other team then can carry forward. So in terms of bringing it to market, for me, like this is the organizational challenge. I know it's kind of maybe not a typical answer, but I think because he insisted on that, I think this is really good to, like there's something called the Conway's Law, which is an organization that produces software tends to produce software that's structured like the organization. So if you have typically like in self-driving cars, you have a perception team, you have a prediction team, you have a planning team, well, you have a perception module, you have a prediction module, and then you have a planning module, right? And then you have the whole kinds of challenges as a manager, which I discovered, which is like siloing, communication across teams, all these kind of things. And as an ML person that's leading an ML team, what I found difficult is that in ML, you want the holy grail for self-driving cars is that they improve the experience. And I think that's one of the biggest misconceptions that people have about learning. If you chat with like people like your grandma or whatever, like about like learning, and you explain them the high level concept, what they immediately think is that the robot learns after deployment, right? So you kind of like your self-driving car might be dumb when you buy it, but it's going to become smarter because you're going to teach it. And that's what machine learning is. And that's not at all what it is, right? That's not at all how it works, right? There's a duty cycle. There's an like you have like you retrieve data, you look at data, you label it, you test it, and then you deploy it. And this can take a long time, right? So this is on some, huge time scale, this might be true, but on the short time scale, it's absolutely not true. So the iteration speed is the key, and this is the challenges with this organization around perception, prediction, planning. Makes it very difficult to have the whole system optimized really quickly from use. And so I think that's the major bottleneck for me as a machine learning person, which is if driving from demonstrations like user experience and things like this, how can we make every system as quickly improving as possible? And this is this idea that we're very big on at TRI called fleet learning, right? Which we don't care just for cars, but for home robots in general, is like, we have millions of evolutions, millions of years of evolution, plus decades of parental education. And machines like a car doesn't have that leisure, right? Like, nobody would buy a Toyota if they had to say, all right, I buy, 6 months old, and then I have to tolerate all kinds of destructions like we were talking about just before recording. No way, right? No way people would buy a car like that, or a robot like that, right? That destroys half the home and then say, oh, it's okay, it's learning, So we got to speed things up, right? So the learning has to be much more accelerated for machines than it is for humans. And the only way to do that is parallelism. And so fleet learning is something we're very, very big on for that purpose. So fleet learning and end-to-end system level optimization and the right organization to match behind, I would say, are the three big bottlenecks to deploy any robotic system.
Interesting. So I guess I kind of think of, machine learning as primarily helping with perception. Am I wrong on that? Do you view machine learning as something that goes everywhere in the
Yeah, so both. So yes, you're right that today perception is the main application for machine learning, at least in robotics. The reason for it is because there's just no way around it. Like ImageNet competition is kind of funny. So one of my mentors and one of the people I admire the most is called Florent Perronin. And he was the head of the computer vision lab at Xerox Research. And he won the ImageNet challenge before deep learning. And in the year of deep learning, people say like, oh, and deep learning, half the error rate. Well, they have the error rate of Florent, which he improved. Like, so every year was improving 2% extra. So there's some kind of inevitability to it. And Florent became like really good at this, and like the lab, and like we all like got into deep learning because, again, we face the evidence as scientists. So it's inevitable because it works so much better. And also because there's no other way. Like, you cannot engineer a world model, because you do this and then you say like, oh, these are the labels I need, these are the features I need, and all these kind of things. And then the world constantly changes. The world is non-stationary. Then you have like scooters. You have like literally humans flying at 30 miles per hour on the street. And you're like, wait, what? Is that a pedestrian? Is that a motorcycle? Like, is that a bird? Is that Superman? Like, what the hell, And so it's inevitable, and it works so much better. So for perception, it's no brainer. Even the most hardcore, like feature engineering passionate people, or people that, believe there's an equation for everything, nobody I know argues that this is the wrong approach to perception. But it's not the solution either. It's not like a slam dunk either, because we need to go beyond that. So I would say robust perception is not solved. Some form of perception, when you know everything, etc., and you don't care for these 9 nines of reliability, right? You can get really, really far. But uncertainty modeling, handling, false positives and all these kind of things, that's a really hard problem. So that's why, like, machine learning, like every abstraction is leaky. So that we're going back to PyTorch. That's why I like minimizing abstractions, because any abstraction is leaky. And the problem with the modular robotic stacks, like perception, prediction, planning, is that you're making abstractions, you're making APIs. And the contracts you're making is like, if you think microservices type of things, they're all statistical in nature. So you're kind of saying, I'm going to give you something that I'm calling a red traffic light. And I'm confident that 99% of the time I'm right. What happens during this 1%? You're on your own, right? And it's unavoidable, right? Because no system will ever be perfect. And you shouldn't require a robot to be perfect. It needs to be better than a human, but it doesn't need to be perfect. Otherwise, you will never ship. So how do you robustly handle uncertainty, and how does it propagate through each layer? And how do you think statistically versus logically or symbolically? And that's becoming harder and harder as you move from perception to prediction to planning, because then planning is actually reasoning, right? It's search, it's reasoning, it's a higher order cognitive function in a sense, and manipulating just feature vectors, like esoteric, feature vectors. It's not really how it works. So this neural symbolic system, the best of both worlds, like I know Marco Pavone is like an awesome Stanford professor that's doing like cool research on that. How do you combine deep learning with more logical forms of reasoning? Something also we're looking at TRI a little bit.
So how does it work today? Like, do you actually send more information? Like, I feel like other people that I've talked to have talked about not just sending the output of the perception algorithm, but maybe even some of the activations of the parts of the neural network before the output. But then I wonder, like, what do you do with that downstream in a sort of logical system? Right. So how does TRI handle that?
Right. So actually, that's not the approach we're taking, because you're right. It's kind of like, yeah, so like you're just pushing the thing under the rug. It's like hot potato game, you know? It's like, oh, I don't have to solve this problem. There you go. And typically it doesn't really work well across teams. It's like, I don't know if this is going to work, but it's your job now, you know?
Right.
So my personal holy grail is like building an end-to-end differentiable but modular system. So still like engineering what you know, but learning what you don't. And so what it means is that you still have a perception module. It still outputs some concepts, you know, like, oh, this is a person, this is, persons exist, roads exist, we know this, right? So the problem is that we're unsure whether our inference about them is right. So here, and my boss, Wolfram Burghardt, which is one of the legends of robotic, because he wrote this book called Probabilistic Robotics with Sebastian Thrun and Dieter Fox, and created this whole movement. It's like, one thing we discuss very often with Wolfram is like, there shouldn't be an argmax, right? If you have an argmax in the middle somewhere upstream, you're basically destroying uncertainty, right? You're just forgetting any uncertainty you have. And what's really interesting is that this is coming from a theoretical perspective, but from, again, like an organizational perspective. If you are the planning team and I give you something and I'm perception, and I give you, this is a red traffic light, and I'm wrong, you're going to be saying, hey, we crashed, it's your fault, you're wrong, fix it. And I'm like, well, but I cannot always be right, and says la la, and you will be la 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 la, right? So this is not how it works. So the things you pass, every data structure that you pass, every information that you pass, right, is a distribution. It's probabilistic in nature. I know I'll sound like a Bayesian crazy guy, but I'm not a Bayesian guy. But like, from just a principled approach, you are uncertain about everything, right? It's a good principle in life too. You shouldn't be like too confident in everything. But so you pass the uncertainties. So very concretely, your object detector, you try as much as possible to not argmax, let's say, over the logits, to say like, oh, this is a person, I'm sure. You're passing the full probability scores. And then you have to handle it downstream. So you have to have a model that doesn't say, if person do this, right? You have to be like, and so that breaks any kind of rule-based system you would have downstream. So you have to digest uncertainty. We have a recent paper at IROS where we showed that, for instance, you can pass a probabilistic perception outputs into an imitation learning, like behavior cloning system. It's with ETH, like Andreas Buehler, an intern of mine. So it's going to be published soon. So passing uncertainty and leveraging uncertainty in the representation for downstream applications. We also have very cool research with Stanford, so with Boris Ivanovich and Haruki Nishimura, like two wonderful PhD students at Stanford, working with Marco Pavone and Max Schwager. And it's interesting, it's like people in robotics and aeronautics, etc. And they're really, really good at thinking about safety and these constraints. And so here the idea was, Boris made a paper called Trajectron plus, which takes in tracks of objects and can output multiple possible future trajectories. And that's great. You can predict the future on that. But the problem with that is that it's very difficult to leverage in a planner. Like, now you can say, oh, I could go left, I could go right, I'm not sure. And then the planner is like, well, but how do I decide, right? And if you're too conservative, right? If you mind safety and you're too conservative, then what happens is that everything is possible. Therefore, you have the frozen car problem, right? It's like, I don't know what to do. Everything is possible. Therefore, I will not move. So then you have a self-driving car, but it stays in the garage, right? Not great.
Right.
So with Haruki, Boris, we basically did a system where we modified some of the control. So like, you have to have very deep knowledge about control, and people like Max Schwager and Marco Pavone are really like super, super smart about this. And this is called risk-sensitive control, where basically what you can do is you can like leverage these different samples from the trajectories and reason in terms of control of, how do I minimize my risk? How do I optimize my objective? Like, I want to drive, I want to go there, right? But at the same time, I want to avoid collisions. And so a really interesting thing is that there's a simple mathematic trick called the entropic risk. And I can refer to something published at IROS, and you can find this on my website, where you can basically change the objective function. So it's almost just a change of mathematical formulation of the optimization problem of how to plan. And you can have a very interpretable high-level variable that's called the risk sensitivity, to say whether you should, if you're risk sensitive, you can go there. If you're risk neutral, you can go there. If you're risk seeking, you can go there. And then the problem becomes, how do you adjust this? And we have like follow-up work on that too. So yeah, it's ML is everywhere, but it's like starting from perception and more moving to prediction. And I think where the cutting edge is in the planning and control side, because we did also some work with Felipe Codevilla and other folks that is now at Mila in Yoshua Bengio's lab, where we looked at behavior cloning, so just learning a policy from pixels to steering. But that is still far from like a very well engineered stack in a domain that you know. So how do you bridge these gaps? So ML is everywhere. Yeah. Of course, I'm biased, right?
Right. And I guess your team sits outside of any of these teams, so it's sort of like going back to Conway's law. Your goal is to put ML, I guess, in every component of the.
Exactly. Yeah, right. So we're trying to find applications wherever possible. And again, the holy grail is that we want to improve the end-to-end system of experience.
And going back to what you said about fleet learning, like how does that work? I mean, what actually can you learn, from the fleet, and how real time is that?
Right. So that's good questions, insightful questions. So you could argue that today fleet learning exists, but it's the disappointing version of it, which is just data haulback, put in a data lake, ETL, label, all these kind of things. Like, so basically anybody that kind of does data science does fleet learning in a sense. So for robots, the whole kind of like spiel, it's like what Steve Jobs was saying is like a 10x quantitative improvement is a qualitative improvement, right? Mm-hmm. And so if you really improve the cycle, like the iteration speed, that's where you're going to get to true fleet learning in the proper sense. So one way is to just make that same process just faster by just optimizing it. So retrieve data faster and iterate faster on it and redeploy the models faster, right? And so that would be, for instance, looking again at this theory of constraints or a theory of lean, look at the bottleneck. The bottleneck is labeling. So that's why we work on self-supervised learning. So being able to do faster and faster fleet learning in this sense would be just get more out of self-supervision so that you can iterate quicker and update the model with less labels. That's the big direction we're doing. Another one is to start to look more towards the holy grail of lifelong and continual learning, where you have things like federated learning and these kind of things, where what you share is not the data, but what you share is, let's say, the gradients with respect to a local objective that you computed, for instance, right? That has some benefits also in terms of privacy, in terms of communication, in terms of many, many things. So you can do lifelong distributed learning in this way, and federated learning, and these approaches exist. Ultimately, beyond just sharing data or just sharing gradients, you would want to share more like useful kind of like concepts, like the distillation of what you learned, right? Not this, because here you're never distributing the learning. You're distributing what enables a centralized learner to then share it back, right? But what you want is to distillize what you learn, like share what you learn, right? And so that's what ultimate fleet learning has to become. It's not completely clear exactly what's the best way to do that, but there's a lot of exciting research on it. There's like super cool research on meta learning, for instance, from Chelsea Finn at Stanford, Sergey Levine at Berkeley. That's exciting. But I think that's one of the exciting research problems is how do you do very efficient fleet learning where what you share is the distilled experience of each robot individually so that they learn as fast as possible.
Makes sense. And I guess I just, it's a little bit of a diversion, but I just wanted to touch on the meta learning a little bit because, you were one of the people that really pushed us to build this Ray-Tune integration that we've actually launched recently. We're really excited about. I'm curious if you could say a little bit about how you think about hyperparameter search and just sort of like the optimization in general. Right. Like when do you do it? What value does it bring you? What strategies do you use?
Right. So I'm a big fan of hyperband, and because just simply this idea of like, first, the formalism is nice. It's formalizing as an online learning problem, like the bandit style. The second thing is I think the best way to be efficient is to reuse computations, and that's exactly what they're doing. And because everything we're doing is SGD, right? Stochastic gradient descent is an iterative process. So having this idea of like continuing optimization of the best solutions and selecting things like this, I think that leverages some unique aspects of the optimization. In the early days, I was using HyperOpt, and I liked it a lot. And this notion of like you model your parameters as random variables, your hyperparameters as random variables you don't know. And so what you do is you sample from them, and then you fit the distribution. When do we use it? Well, that's a hard question, actually. That's a really, really hard question, because when you're in production, you use it whenever you're about to deploy the model. You have some good confidence that this model is working well, and now you want to squeeze a little more out of it. And you have a clean protocol, right? Train, val, test, set, split, or you do something a bit more sophisticated than just a good split. But already a good split it can go, when you build your own data sets, if you build a large validation set, a large test set, and it's diverse, and you're good at building those data sets, then that brings you a long way. So in production, I think the answer is easier, but in research, it's hard, because in research, you're like, Is it not working as well as I intended because I have a bug? Because it's typically more fresh code, right? Like production is like the code has seen more pairs of eyes and more iterations, but in research it's more fresh. So is there a bug? My advisor kind of like Cordelia Schmidt actually taught me this during my PhD, which is whenever there was something funky, you ask yourself 5 times whether there's a bug, and so it's like and it's funny because I discovered that there's this exercise in safety, in critical analysis called the 5 whys, and you think asking why 5 times for when there's a fault or there's a problem, you think 5 times, easy. By the 3rd time, you're like, oh, this is hard, So is it a bug or is it just a hypermeter search problem? And so typically you want to start like hypermeter search is kind of a hammer or a bazooka. You don't want to use it to kill a fly, right? So I tend to try to delay the use of it when I believe that's the source of the issue. So that would be my answer.
Yeah, it's interesting. We've gotten very strong reactions both ways, I think, in the interviews that we've done. I mean, some people are like, oh, hyperparameter search keeps you from actually learning the underlying structure of what you're doing. And other people are like, why would you, spend any time figuring out what hyperparameters you want? Just let the machine do the work. So it's interesting.
Yeah. I think there's these 2 phases, right? Like you start to develop the intuition and you experiment with it, because anyway, hypermeter search is not magic. You have to decide the ranges of your hypermeters, right? Or even if you use Bayesian hypermeter optimization, you have to decide even the probability distribution. Is it the log normal? Is it these kind of things, right? And the bounds. And it's typically an iterative process, right? You do a first guess, you realize, oh, my optimum is on the edge of, if you do grid search, on my edge of my grid search. Okay, I need to extend it, right? And so you iterate on that. So it's still not in my experience, maybe more on the research side, it's not like, oh yeah, and now hypermeter search, done. It's not like this.
Right. Well, all right, cool. We're running out of time, and I always like to end with 2 questions for consistency, and maybe we can do some analysis on the answers one day.
Oh yeah.
But here's the penultimate question that we always ask is, what is an underrated ML topic that you think people aren't talking about as much as they should for how valuable it might be? Right.
I would say the things that we mentioned earlier was like how little machine and how little learning there actually is in machine learning. I was having a nice chat with Shivan Zilis, and she was saying, I'm interested in machine not learning. And I liked how she phrased it. I think, there's more seriously this bigger concern around ethical use of AI and all these kind of things, right? And there's always this saying of like, because you could doesn't mean you should, right? And so the question in machine learning is very much that I think is interesting is what should not be learned. And so there are certain applications that should not be pursued, things like classifying, like, I don't know, like justice, like illegal applications. We've seen all kinds of horror things, especially computer vision. Sadly, there's a very easy way to. So there's just applications you shouldn't do. And I think is a leading researcher on these questions. She has done a great tutorial, I think, with Emily Denton at CVPR this year, which I can recommend your readers to think about this more socio-technical challenges there. But in practice also, in more like once you work on a good problem, like, saving lives of self-driving cars or helping people age in place with home robots, and you should do these kind of applications, then the question becomes like, which part of my system do I design? Which part of my system do I learn? And this is tricky because like you need some design to generalize. Because if you try to learn everything, like the example, like James Kuffner, was former CTO of TRI and the head CEO of TRID, was basically telling me like, you don't drive in front of a school 1,000 times and risk bumping into kids to understand that the limit is 25 miles per hour, right? So there are certain things you need to engineer, but there are certain things you need to learn. Where do you set that line is very difficult. And the second answer would be labeling. It just, if you listen to anybody that's talking about self-driving cars or everything like this, and AGI and all these kind of things, never ever do they mention labeling. Like, and if you know what's happening behind the scenes in the industry, is that this is what is going on. This is what learning is. That's what I said. There's very little machine in machine learning because it's human labor. It's a tremendous amount of human labor, like hundreds or thousands of labelers today. Right? You don't have self-driving cars, and yet we have thousands of labelers for a single like application that are just clicking on pixels, and you know about this, right? It's actually you must do this. My take on this is that you must label for the testing purposes, but as much as possible, I would like to avoid labeling for training purposes because the training has to be continuous. So that would be why I think labeling is just surprising how few people are talking about it in the industry, the costs and the scalability issues that go with it.
Interesting. All right. Well, I could ask questions forever about that, but I want to ask my final question and wrap this up. So what is, in your experience, the hardest part about taking models and getting them deployed in production and used? Where are the big bottlenecks?
Right. Scalability is such an obvious answer, right? Where, in the research land, we have this idea, we have this prototype, we use a standard data set, or even build our own data set, right, to prove an idea. And then you have first like a human element to it, which is you have to convince people to run with that idea, and that should be enough, right? You should have a nice W&B report, and they go, yes, awesome, we're gonna put like 20 or 30 or 100 engineers on it just based on that. So there's some amount of convincing people like to go from research to production. So you have to be compelling, enough compelling evidence. That's more on the researchers' end. Like our bottleneck is to convince people, and part of it is the scalability, right? So people might say, I understand the idea, I can see that this works, like your evidence that you present, but I don't think it's going to work in this scenario, or I don't think it's going to be cost effective, or I don't think it's going to be easy to just scale up, like computationally speaking, or something like this. So worrying about scalability is something we really do. So one of the things that I did earlier this year is that so we kind of split the efforts in the ML team between research and engineering. And Sudeep Pillai is now the head of ML engineering at TRI. And he's really driven to this. Like whenever I talk to him, like it's like really that's his drive, is that how do we think about scalability? And he's doing really cool work with his team on semi-supervised learning and these kind of ideas to try to scale things up so that we can go from research ideas that maybe not scalable to like more well-formed, transferable research idea that is shown to work at scale already at this stage, at the prototype stage, and then that can maybe be transferred.
What does it mean for an algorithm to not be scalable?
Right. I mean, for instance, labeling. If you say, yeah, I can get to great performance, I can get to 80% with a data set this size. And then you look at the performance improvements with the training set size, and then you realize that the improvements are logarithmic. And this is not good, right? You say, oh, it improves with data. That's great. But it's then your cost is going to be, all right, you need $1 billion data set. You don't really want to do that. And $1 billion compute, right? This is a bit like the OpenAI story, which is if you have infinite money, infinite labelers, infinite time, infinite compute, how far can you go? And it's super interesting to see these guys, like it's amazing what they do in terms of pushing the boundaries on that. But for like some applications in the real world, that's not really reasonable. So you have to kind of think about how do you scale. And we're not trying to solve everything at once. So really for us, the compute is something we kind of ignore for now. We're saying, let's assume you have infinite compute, but you don't have infinite labeling budget, right?
I was going to say, we've seen we see OpenAI's usage and your usage is not small.
Yeah, I'll take it as a compliment. No, we're well funded and we're utilizing it well. So computation, right? Again, I said like not enough machine in machine learning, but that's what we're trying to do. We're trying to make machines work for us, right? It's kind of funny how people are saying like, it used to be that humans play video games, but and then they do work, but now it's kind of like, we work so that machines can play video games, like we make algorithms that can play Atari while we don't do Atari games anymore. So that's weird.
All right. Well, thanks so much, Adrien. It's so much fun to talk to you.
Likewise. It was a pleasure.
Thanks for listening to another episode of Gradient Descent. Doing these interviews are a lot of fun, and it's especially fun for me when I can actually hear from the people that are listening to these episodes. So if you wouldn't mind leaving a comment and telling me what you think or starting a conversation, that would make me inspired to do more of these episodes. And also, if you wouldn't mind liking and subscribing, I'd appreciate that a lot.